Alright, draft physics video presentation. Still on photons and such. So I guess I'll start with just a little bit of a premise. As I learned about photons through my life, there was never made a very good explanation of what really photons are a byproduct of, so I would argue that it's heat. Okay, so you make something hot and it produces photons. It's a pretty safe relationship that exists, and the hotter you make it, the bluer, the tighter the frequency, the faster the vibration, if you want to call it that. So the idea is, in the universe, I would argue, is that there's pressure, and pressure is essentially a kind of heat. So if there's something bouncing around inside of a box, you could say, you can sort of understand that the smaller I make the box, that is, I make it more pressure, that the faster the thing's going to hit sides and have interactions. So there's just plainly more interactions, twice as many impacts. The cars, like in a demolition derby, bang into each other a lot more often. So if I make the field that you're banging cars in smaller and smaller, I make the likelihood that the cars hit each other higher and higher. Now in this case they're hitting the wall, but same difference, you could argue. And then substances are essentially made of these little boxes inside of boxes inside of boxes inside of boxes. And the boxes are bouncing around, also doing the same thing, hitting things. So the big box, the smaller the box gets, the more the boxes bang into each other, the more the stuff inside the boxes bangs into each other. So it's really just, the rule is basically you just have to have a source of either something that makes the box smaller or something that puts more cars, okay, inside the box. And it'll reach some sort of equilibrium, and cars will fly out at some rate. So if you have a rate of stuff going in, then you have a rate of stuff going out, and but there's still a pressure inside the box that exists. And the higher I make that pressure, that is, the more heat I pump in, the more likely that I'm agitating the edge of the box quite aggressively, that it's getting hit a lot, that the frequency is going from something like this in terms of how it's getting hit to something much higher. And that is what we see as a photon, in the sense that the outside of the box is constantly moving. And if you could theoretically understand that there's still a bigger box around the box, you'd understand that as this box surface moves from this position to, say, this position, vibrating, that would be hitting this pressure. That would mean that it would be under high pressure 1 minute, that is, having more interactions, and then less interactions when the box surface is over here, and that the pressure inside of here would also reflect the pressure that was in here. So whatever vibrates here is going to vibrate the stuff in here, in the sense it's going to change the distance it's moving. So 1 minute it's moving like this, the next minute it's moving like this. And so this vibration, this movement, is going to be conveyed to this surface and cause it to move likewise. And in a sense, what's conveying it is the photon. The photon is the force. It's not a thing, a particle, so to speak. It's, I would argue, hard and moves at the speed of light, a constant speed, and never dies. It's the mechanism. You can just move it around. You can just move where the pressure is. Based on where you put these photons, they will, through the interaction, be conveyed in terms of causing action somewhere else. And it's essentially an exchange of that momentum. But this is the carrier of anything you want to call a field or whatever. That's what photons are. The photons they aren't a byproduct of an electric and magnetic field. They are the field. And the ones we can see, the ones that are at the right frequencies, we call those light or electromagnetic spectrum, but they're also gravity and magnetism and in some form electricity. I mean, electricity is a special case where clearly that's an atomic function. That's something conveyed from one atom to another atom to another atom, and without atoms you don't have electricity. But clearly the movement of atoms is magnetic, I would argue, certainly. So anyway, it's just a way of looking at it that I think is more rational than the silly wave thingy. In the sense that this is just momentum. It could be understood perfectly rationally as space being full of a bunch of little bits, BBs, and that matter, electrons and protons, form surfaces that are moved by being hit by the BBs. Nothing more complicated than that. Ping pong paddle, ping pong ball. If I move the paddles closer together, that's pressure, and the result is the ball hits surfaces more often, and that we call heat, because the consequence of hitting those surfaces is you're breaking them. Alright, cracking them, distorting them, changing them, and changing how they interact with whatever on the other side of them. Okay, yeah, enough background.
Don't miss a moment.
Well,
Live TV from
we don't
70
care
plus
for that.
channels. YouTube TV. Start streaming now.
Yeah, right.
See that bright brain full of activity? That's a
Nazi
healthy
TV.
18-year-old brain.
YouTube.
Mine is the other one.
In order to understand the photon better, let's now take a look at the oscillating magnetic field and electric field inside the photon. Now let's start with...
So again, inside the photon, he just said, which doesn't make any sense. And again, the field is the photon. The photon makes these things. It is the force. It's one of the forces. You can have the force in the form of magnetism, charge, or in the form of visible spectrum light that happens to be at a frequency. So you can have the force where it's not frequency dependent, creating gravity and magnetism, or you can have the force that has a frequency dependence where it's oscillating at a consistent rate because of these interactions. Just as this, no matter what frequency this would be, in terms of I'd have stuff trapped and it would be bouncing, this would clearly be twice the frequency.
The magnetic field effect of a photon. So imagine a photon is flying through space at the speed of light, v is equal to speed of light, and of course realize that it will have electric field oscillations and magnetic field oscillations which are perpendicular to each other. So in that case, we have an electric field that's oscillating like this, magnetic field that's oscillating like...
It's very cute, but again, and there's just no explanation for how the field knows to oscillate in these two different directions. No explanation at all.
this. So
And again, it's the obvious answer is the photon is those fields.
that's how a photon moves through space. Now what happens when a photon like that meets up with an electron? Now the effect is as if the electron is...
So again, no photon meets up with a single electron. It just doesn't happen. The energy is in a form, where it's bullets fired at a frequency, and lots of guns are shooting the bullets. And the bullets fly through space, and individual bullets interact with individual electrons, but they can't do anything as individuals. It's just one bullet hitting an electron and moving it. What has to happen is the bullets have to all hit electrons at the same time and move the matter, the atoms. And usually in the form of crystals, they have to move a whole series of atoms to create a surface that's now moved. And once the surface has been moved, and it will tend to move back because it's attracted to the other atoms through this pressure mechanism. When it moves one way, that means it creates less pressure behind it, and there's going to be a tendency to move back into that pressure, and when it does, it's going to steal energy essentially from the external world. By moving away from something, I create a low pressure.
Flying towards this, if you imagine for a moment, better to look at it this way, that this is a stationary photon. Of course, photons cannot be stationary.
See, the reason why it's better to look at it this way, he's saying, is because they don't have any good explanation for what they're claiming, which is motion this way and forward, when all they really have is the forward momentum. They don't have any motion this way, and they don't have any motion this way. They just have momentum in one direction. And so you can't explain it by saying, well, look at this three-dimensional motion in 3 dimensions that I'm sending, and then I'm going to claim to have a single interaction with 3 different dimensions at once. So that's hard to make sense out of. So he's going to give the momentum to the electron, and then he can ignore the motion of the photon, because the motion is so much different than this and this. This and this doesn't mean that, kind of thing.
Move through space at the speed of light. But if for a moment imagine that we change the relative coordinate system, so that the coordinate system is moving along with the photon, and then we have an electron that seems to be moving towards the photon at the speed of light. Now, there's going to be an effect between the charged electron and the oscillating magnetic field. So, imagine that the photon is flying in this direction at the speed of light.
So again, this doesn't make much sense when you really think about it, right? Because if he had to do this in the real world, then he'd have to claim that the electron... Oh, he's doing that. He'd have to claim that the electron was gaining momentum in more than one direction, that the magnetic field was moving it this way, that the electric field was moving it this way, and that the momentum of the photon itself was giving it a momentum in this way. And that's not what electrons do. They don't gain 3 different momentums.
So in this case, we're going to say that V is equal to C of the electron. And we use the left-hand rule because the electron is a negative charge, and so we point our fingers in the direction of the velocity of the electron towards the magnetic field that's oscillating, going up and down like this. Or no, actually, it's going sideways, isn't it?
So now he's talking about the magnetic field, and he's just ignoring entirely the electric field, when they say most of the time the electric field is the dominant field. So again, frankly, I can't make any sense out of that. So clearly the photon, he's sitting there doing this right-hand rule with the magnetic field. All of a sudden the electric field is irrelevant to the electron. So I thought the electron was supposed to be the electric monopole. So why isn't it being affected by the electric field, not the magnetic field? Oh, that's right, because the electric field is moving up and down. There's no fun there.
It's going sideways. So here we have the electron going this way. Imagine that we look at this portion of the photon where the magnetic field is to the left. So that means we point our fingers in the direction of the motion of the electron. We turn our hands so we can now point in the direction of the magnetic field, and we can see then that the force on the electron is downward. So let's write that here. So when the electron is, for example, right here at this point right there, it's experiencing a force downward. Now.
All right. So this is sort of an interesting subject. This is going to come up in the subject of, I plan on doing a video on cyclotrons and superconductors, super cooled materials, and blah 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 blah, because it really is layered in all of this right-hand rule stuff. And so just to point out that my theory already accounts for all of that and is perfectly consistent with those results and blah 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 blah. So the idea I've tried to emphasize is the electron is a thing that has a history, okay, and all it does is it makes exchanges. So if the electron force hits it, it makes an exchange. That is, an arrow going this way is exchanged, okay, for an arrow, let's just say an arrow, is exchanged. And the tendency is obviously going to be to hit stuff coming towards you rather than stuff that goes away from you. So you're not going to be able to exchange this for this. You're more likely going to exchange it for something coming towards you, something in that direction, something that could be going this way. And the point is that it's just an exchange. So whatever is the dominant thing in here, the most likely to hit, is what leaves, and this ends up in here going this way. So if this was a net exchange, you can understand if it lost this, okay, this got lost, and it gains this, that it's really a 2x increase in velocity in this way. A 2x change in, you can call it acceleration. The point is if it was going 4x this way, then obviously it's only lost 2x, and it's still going 2x this way, right, if it was going 4x this way. But I'm just saying, you're changing the velocity, and it's going to be a 2x in terms of quanta change, even though it was only one interaction, even though you have force in, force out. That's just the nature of these beasts, is this is what they're doing. They're exchanging. So they're not consuming anything, they're just making exchanges. Now, the only thing that can get exchanged is the only part which gets a little tricky. And again, this is all just based on a theory of understanding that there's only a small range of possible interactions in the 3 dimensions. So you always have to understand there's 3 dimensions, which is irritating. Maybe put this one in bluish. And what you're saying is you have energy coming in, say, 2 ways, and you're going to have energy coming out in 2 ways, which could be this way and this way, or it could be that way and this way. So you're just really saying that you can have interactions where 2 things hit each other, right? And you can sort of understand that that could mean that both things go this way. It could mean that they just, one thing goes this thing turns right and goes this way, and this one goes straight. Or if they were different colors, you could understand that, you know, this one goes this way and this one goes that way. You know, so there's lots of ways you can recognize that the exchange, the interaction, can have nuance to it. So the point would be is that in the case of this opposite force hitting, okay, so an opposite force hits the electron, the proton force, that the interaction would be different than that pure exchange, and that now the interaction is going to do this dimensional change. So it's not going to produce the momentum in the same dimension, and so energy will go in this way. The exchange will be made with whatever the easiest to hit thing is, let's argue. But for this case, let's just say it was going in, say, the left direction, okay, into the board arrow. And so that's what I hit. Well, coming out of the board, doesn't really matter. So I hit something coming out of the board. So there's an arrow inside this thing going this way towards you. All right. And that's the one this thing hits, or exchanging with. And the byproduct of that exchange, though, is this is kept inside. It gains momentum this way, and it gives back the force this way. So the right turn is in the other dimension. So it's hitting something, say, going this way towards it, or out of the board, and it bends that this way inside. Is the one that stays inside ends up going that way, and the one leaving takes this right turn. So there's been a 90-degree shift in the 2 momentums. So you still have a consistency in that they've both given away the same degrees of momentum, and that's legal in the universe, so to speak. And so that would account for this motor force. So do I want to say anything more about that? No. So you have these 2 different interactions, and it just depends on what you're hitting with what force. You know, whether you're hitting electrons with the force that makes the more consistent in the same dimension exchange, or the one that makes an interdimensional exchange. I guess that's a way of putting it. Yeah, so regardless, what the point to make is that electrons, when they're moving, the difference between an electron that's just sitting there and an electron that's moving, okay, is the fact that you have to kind of see it as if I was to draw its profile, what it's trapped. So let's say it remembers 20 events that happened, 20 interactions with the universe, and that's what it holds inside of it. It has 20 seats. There's something always sitting in the seats, some arrow. The arrow comes in, exchanges the seat, blah, blah, blah. So you can understand that as it's moving, that means it has a bias in a direction. That is, it has more arrows going that way. So the faster you're moving it, it means there's more arrows going that way, a lot less going this way, maybe 0 going that way, and not too many going that way either. So its net motion in space is being dominated by its motion. So if I theoretically moved it the speed of light, then it would have all of its fish. It would be a school of fish with all the fish swimming in the same direction. And the slower I make it move, the more it's like a school of fish where the fish are going in all kinds of directions and they're just kind of staying in one place. Even though they're all swimming, the whole school itself doesn't go anywhere because there's fish going this way and fish going that way at the same time. And the difference for an electron is as it's going, as it starts moving, well, it's the same as the school of fish. As it's moving, it's predominantly becoming one kind of arrow. So any interaction with the external field, any exchanges, are going to be exchanges for these fish and in the direction, well, you can't see that last arrow. So the exchanges will happen with its momentum. So its momentum will change. So what you can sort of understand, well, I probably shouldn't change subjects, is that the motion that in a magnetic field where you get this spiraling motion is really just the fact that its velocity is fast this way. It's making exchanges, okay, with a magnetic field running through it, which is converting the motion into this direction. And then it's still making exchanges, which converts its direction into this direction. And so it just keeps doing that. And that's why it's spiraling, because as it gains momentum in a direction, those are the fish more likely to be killed and turned into fish going this way, and this way, and this way. So its dominant velocity becomes this velocity. And then as that becomes the dominant velocity, its dominant velocity will be changed to this velocity. So if you're in an even field of exchanges, your exchanges will keep making this right turn because you're going to keep killing these arrows and replacing them with these. And so on and so on and so on. Enough. Yes, squeaky chair.
What happens when it meets up with the magnetic field that's now in the opposite direction? Again, we use our left hand, point our fingers in the direction of the motion of the electron, the envisioned motion, of course. We turn our hands, point our fingers in the direction of the magnetic field, and now our thumb points upwards. So we can say that if the electron is here relative to the photon, then the force will be upward. So we can see that the electron will feel a force oscillating up and down as it's passing the electron. So as the photon...
So that's very convenient, but it's also feeling the electrical force, you would argue, that's doing some kind of similar thing. And doesn't that all come out to nothing? And what the electron's really going to experience is momentum in a direction. It's going to move.
Photon zips past the electron will feel a force up and down, then up and down, which will cause the electron to oscillate up and down at the same frequency of the frequency oscillation of the magnetic field in the photon, which is the same as the frequency of the photon period. So
yes, and that doesn't make any sense, because to do that it has to go through many nodes to go up, and then to go down is another node, and then another node, and another node. And what would that accomplish? You're just moving the charge up and down, okay? For what purpose? To duplicate exactly what went in, with no motion, no forward motion. So again, it just doesn't make any sense. It's not just bouncing up and down, it's moving. It's expanding the box.
This is how a force will be felt. Now, what would be the strength of the force? Well, let's go ahead and figure that out. We know that the force on the charge caused by a magnetic field is equal to QVB. So now the question is, well, what is the strength of the magnetic field? Well, assume for a moment that the field is
Q is the charge, right? So again, they're combining the two, which you have to, because they've defined these things with the mu zero and epsilon zero, the bisecting of the speed of light. So what's really in here is the speed of light, just bisected into Q and B.
Caused by sunlight approaching the Earth, and it meets up in electrons. So with sunlight, we know that the intensity of sunlight is equal to 1361 watts per square meter. And we also know that the intensity, which is equal to the Poynting vector, so the intensity is equal to the magnitude of the Poynting vector, which is equal to 1 over 2 mu sub naught times the strength of the magnetic field, max, the maximum strength, times the maximum strength of the electric field. Now, when I say maximum strength, I mean the maximum amplitude of oscillation.
Yeah, you mean you're converting it into quanta. You're one thing, not a gradual anything. You're turning it in. This is just basically saying clump. Okay, that's what it's saying. And then he's got the mu zero stuff in here. So it's the same BS.
Now, that's not a physical amplitude, it's simply an intensity amplitude, if you want to call it that. We also know that the relationship between the B field and electric field inside a photon can be written that the electric field is equal to the speed of light times the B field. So this can be a vector, this can be the magnitude, and this can also be the
So that's just the frequency argument again.
Maximum amplitude of that B field, the magnetic field, and the electric field. All right, so what we want to do is we want to find the strength of the electric field and the strength of the magnetic field inside this photon, which came from the sun. Let's say that it's a photon coming all the way from the sun, so that the sunlight has an intensity of 1361 watts per square meter. All right, so what we need to do then is we need...
So the photon obviously doesn't hit a square meter at 1361 watts. So there's just no single photon doesn't have that wattage. So he's talking about the rate at which all the photons are hitting. And so again, he's pretending he's doing the relationship between a single photon and a single electron, and then he's converting the equation into what do a million photons do covering a certain area.
To find the strength of the electric field. So if I now plug in that B is equal to, well, first we'll find the electric field strength, and then we'll find the magnetic field strength. So even though we're talking about the magnetic field effect, and I should put a D here, field effect right there, we're going to find the strength of the electric field, and then using this equation, we'll find the strength of the magnetic field, and then in the next video, we'll compare that to the effect of the electric field. All right. So this can now be written as E over C. So the intensity is equal to 1 over 2 C mu sub naught times E max squared. So therefore, E max is equal to the square root of the intensity times 2 times the speed of light times mu sub naught. All right, plug in some numbers. That's equal to 1361, that would be watts per square meters, times 2 times the speed of light, 3 times 10 to the 8 meters per second, and times mu sub naught, which is 4 pi times 10 to the minus 7. And of course, when we take care of all the units, we'll get volts per meter. And I'm looking for my calculator right here. So we have to...
So it's the square root of something squared, which is, kind of circular.
1361 times 2 times 3e to the 8 times pi times 4e to the 7 minus equals, they take the square root, and they get 1013. So E max in sunlight is equal to 1013 volts per meter. All right, now finding the B field, notice that the B field strength, B max, is equal to E max divided by C. So we take this quantity, divide by C, so 1013 divided by 3e to the 8, and we get 3.38 times 10.
So again, he starts off talking about a single photon hitting a single electron, converts it into millions of photons, and then I'll just do the calculation for the millions of photons back to one photon again. As if this model works, and it doesn't. It only works if you recognize, oh, these are clumps at a frequency, which his math does.
The minus 6, and that would be, the B field, of course, would be in terms of Teslas. So now we established the strength of the electric field which is equal to this, and the strength of the magnetic field, which is equal to that inside a photon coming from the sun. Now, the force on an electron as sunlight passes by an electron, which causes electron to feel an oscillating force going up and down, is equal to the charge of the electron, which is 1.6 times 10 to the minus 19. The effective velocity of the electron relative to the sunlight would be the speed of light, which is...
So again, they're really just, well, I don't know what to say, really, you know. Clearly the momentum is in one direction from the photon, and all of this doesn't really have anything to do with that fact, that the momentum is in one direction. I mean, that's the momentum the electron's going to gain, is the forward momentum.
3 times 10 to the 8. And now the strength of the B field we found to be 3.38 times 10 to the minus 6. And so that would be the force felt by an electron as a photon rushes by it. Okay, let's see what that's equal to. Times 3e to the 8 times 1.6e to the 19 minus. And the force would be equal to 1.62 times 10 to the minus 16 newtons. So 1.62 times 10 to the minus 16 newtons. And so you can see that the electric field oscillations inside a photon, inside electromagnetic radiation, specifically inside a photon, causes a force effect on a charge, in this case an electron, as it rushes past the electron. It has the effect as if the electron is rushing past the light, and you can see that the force will oscillate depending upon the direction of the magnetic field as a photon rushes past the electron. And so that causes an oscillating force on the electron as the photon rushes by. That's
the only oscillating force that matters is the expansion and contraction, the momentum, and in a direction. And so you're just expanding and contracting the distance between electrons and protons, and then you're expanding and contracting the distance between the atoms themselves, and that is the creation of the frequency that the rest of the world feels, because there's always pressure on everything. And if I automatically expand and contract, you could sort of understand that any energy that was hitting me from the external world, even light, you'd understand that as I expand and contract, then my reflection would expand and contract, and therefore I'd be imposing a frequency. My expansion and contraction frequency would be imposed on the light that left. So even though the light has its own frequency, the photons would change based on the fact that the surface I'm creating, that the light would be reflecting off of, is also changing its position. And it's just changes in position being conveyed, because changes in position are pressure. If I bring two paddles together, it means I've created less pressure on this side of the paddles and more pressure in between the paddles. And that's always consequential.
The force. Now, in the next video, we're going to do the same thing, but now we're going to look at the electric field effect on the electron to see what the comparison is between the two, and you'll be very surprised with the results.
Yes, yeah, this is just mush. Okay, this isn't how it works. This just works in the sense that going through all this garbage, they come up with the outcome of an increase or decrease in motion. That's all it comes down to, is the photon imposes momentum on the electron. The electron's momentum is something that has a consequence in terms of creating voltage that we can measure. That's all this is. Alright, so enough of the video, and till the next time, such. Yeah, I think that's it.